Good morning. Welcome to this eighth lecture on univariate time series analysis. So, in the previous lectures, we have introduced stationary time series models such as autoregressive of order 1, then autoregressive order 2, in general autoregressive order P, and then we have also introduced the moving average models such as MA1, MA2, etc., MAQ. We also studied white noise process and non-stationary process such as random walk models. So now today's lecture we are going to discuss little general time series which basically combine the autoregressive and moving average, and then we that yield a new model what is known as autoregressive moving average model. So let's look at this ARMA, which is known as ARMA. So let's see what is an ARMA process. So an ARMA process is given by is defined is xt equal to phi1 xt minus 1 etc plus phi p xt minus p plus zt plus theta 1 zt minus 1 plus. So you can see that this is the moving average part and this is the autoregressive part. So basically combine both of them to yield what is known as ARMA PQ. We may write them in terms of polynomial. So you have a phi b xt equal to theta b zt, where phi b is 1 minus phi 1 b minus phi 2 b square, etc. Phi p b to the power of p, where b is the backshift operator. And theta b is a qth degree polynomial, 1 plus theta 1 b plus etc. theta q b to the power of q. So this is the polynomial, AR polynomial and MA polynomial. Now, what is the advantage of going like this or going for a model which is combining AR and MI? So sometimes what happens that we have the AR order is quite large. So we can actually get a parsimonious model. Parsimonious means in terms of lower number of parameters, less number of parameters. So we can get a parsimonious model by considering ARMA 23. So instead of AR 11, you can go for ARMA 23. I'm just giving a simple example. So ARMA 23 have output 5 parameters, where AR 11 means it has got 11 parameters. So it is possible to do such kind of things. This is subject to the data. Okay, so don't think that ARMA 25 is or ARMA 32 is always equal to AR 15. There is nothing like that. But sometimes it is possible to represent the data with more parsimonious model, and which basically ARMA is combining both AR and MA. So now let's look at this model little detail. So before getting into more details, we consider a simple case where P equal to 1, Q equal to 1. So an ARMA 1 model is defined as xt minus phi xt minus 1 equal to zt plus theta zt minus 1. This is with our usual notation. And we can show that by repeated substitution, it is possible to show that xt equal to zt plus theta plus phi summation j equal to 1 to infinity phi to the power of j minus 1 zt minus j. Now this is just a notation. If you want this to exist, because this is an infinite sum, we need to have a condition absolute of phi less than 1, which means that you can have a stationary solution of an ARMA 1 possible only if absolute of phi less than 1. In fact, it is causal also, because you can write in terms of the current and past values of zt. So that's what this shows. So you have xt equal to, if you could able to write like this, we can call xt as a causal process, but this requires a condition on absolute of phi less than 1. Now how this is written, that's not a big problem, so I'll just show you how this is done. So sorry. So for example, if you write xt minus phi xt minus 1 is equal to zt plus theta zt minus 1. So what you need to do is that I'll write xt as phi xt minus 1 plus zt plus theta zt minus 1, and this phi, now I will write xt minus 1 as, so you can write xt minus 1 as phi xt minus 2 plus zt minus 1 plus theta zt minus 2 plus zt plus theta zt minus 1. So this, if you simplify, you will write phi square xt minus 2 plus zt minus 1 phi plus theta zt minus 1, and then you have theta zt minus 2 plus zt, right? So this again you can write it as, I'll write one more step, xt minus 2 is phi xt minus 3 plus zt minus 2 plus theta zt minus 3. Right, 1 less than that, so xt is, yeah, so this you have. Then you have phi plus theta zt minus 1 plus theta zt minus 2. Oh, this is not theta. Actually, here there is a phi, because you have to multiply by this phi. So I have a phi here. Okay, plus zt. So what is that you can write? You can write phi cubed xt minus 3 plus. Now if you look at zt minus 2, you have phi square plus phi theta into zt minus 2 plus, okay, then you have phi plus theta zt minus 1, then you have so this is we've written this zt minus 2 we have written, then you have phi theta, sorry, phi square theta zt minus 3, and then you have zt here, right? So I think I've taken all the terms now. So if you now look at this, so I have phi cubed xt minus 3 plus phi into phi plus theta zt minus 2 plus phi plus theta zt minus 1 plus, now you have phi square theta zt minus 3 plus zt. So this, if you again simplify, you are going to have, continue to do this. So if you continue to do this, you will reach this equation zt plus phi plus theta. This is constant because this is constant, and summation j equal to 1 to infinity phi to the power of j minus 1 zt minus j plus, yeah, I think that's it. So if something has gone wrong, okay, let's, this is phi theta zt minus 2 phi square theta zt minus 3, yes. So this is actually, you now next time when you get this will be combined over there. So phi square theta, so you have here phi theta zt minus 2 phi square, this comes here, and phi theta come from here, okay, and next one you will have similarly phi square theta will be there, so that will be added up to this. So this is actually reducing to this. You can simplify because see, for example, this is the set t which is coming over here. Of phi plus theta is coming out to be common. This term will absorb in the next time because you will have a term phi square theta. So I'll removing that phi square outside. So you will have phi plus theta again. So this will have phi square theta, phi theta, sorry. So that will be coming out of this. So basically this get combined, and then the power of v will become more and more here. So this is what zt minus 1, zt minus 2, next you have zt minus 3. So from that term actually coming from here and a term here, that comes from substituting over here. Okay, so ultimately this whole thing can be written as j equal to 1 to infinity, this one, j equal to 0 to infinity, because there is a zt, psi j zt minus j. Psi j, you have to pick down the terms from here. This all together will form psi naught, psi 1, psi 2. So psi naught is means just 1, because uh, the reason being that psi naught is actually coming out to be zt's coefficient, and that is just 1. Then you will have psi 1, which is coming out to be zt minus 1's coefficient, and psi 1 you can see that it is 5 plus theta into, if you put 1 here, this is 1. So the coefficient is coming out to be 5 plus theta, etc. So essentially speaking, you have this kind of a representation, and that is called the causal solution of an ARMA 1-1. So basically what you have done is you have written xt as an infinite moving average process. So the above representation is known as infinite moving average representation. Now what happened, as I mentioned earlier, this particular stuff is valid only for absolute of phi less than 1. Now if it is absolute of phi greater than 1 also, you can get a solution, but then the solution is not causal, in the sense that it is going to depend on the future. Like what has happened in the AR case, the same thing is going to happen in the MA case also. So you get a non-causal solution. Then when phi equal to on the boundary, when phi equal to plus or minus 1, actually no solution exists for this particular sequence. Let's now start computing the mean and variance of this ARMA 1-1. What is the mean and variance of this ARMA 1-1? Now I assume that it is stationary, because that's very important to compute the mean and variance. Because if it is not, if you're not assuming that stationarity, then you may have to actually go back and then start working on this infinite sum for the mean and variance. So that's, we did that exercise in the case of ARMA model. So now here I'm just assuming stationarity. So assuming the stationarity, it is possible that you'll be, sorry, in the next slide, able to find the mean and variance. So how will you find the mean and variance? So you have the process is this. So if your process is xt equal to phi xt minus 1 plus zt plus theta zt minus 1, so variance of xt, or mean of xt is actually 0. Now assuming stationarity, we have this is equal to 0. Why? Because we want these two terms to be equal. Now these two terms can be equal only two ways, either phi equal to 1 or phi equal to 0. But phi equal to 1, we have a dangerous situation. We seen that the convergence will not happen. So there cannot be an xt like that. So the case is absolute of phi less than 1. So when absolute of phi less than 1, the only possibility that can happen is phi equal to 0, because otherwise this will not be equal. So mean is 0, and variance of xt is equal to phi square variance of xt minus 1 plus 1 plus theta square into sigma square, and covariance between this is 0, and then you also have a covariance between phi theta and covariance between xt minus 1 and zt minus 1. So this gives me the variance of xt. So variance of xt is equal to variance of xt minus 1. So we can see that variance of xt is equal to 1 plus, this is actually sigma square plus theta square sigma square. So sigma square into 1 plus theta square plus, you have phi theta and covariance between this xt minus 1 zt minus 1, the whole thing divided by, so I'll write covariance between xt minus 1 zt minus 1 and the whole thing divided by 1 minus phi square, because that you got from here. And you can see that the covariance between xt minus 1 and zt minus 1 is equal to covariance between, what is xt minus 1? Phi xt minus 2 plus zt minus 1 plus theta zt minus 2. So this, you have to take the covariance between this. So now you can see that this is one step ahead of this. So this covariance is 0. So that is 0. Plus this covariance is actually the variance, which is sigma square. Plus this covariance is 0. So this is basically turned out to be sigma square. So now you can see that this variance of xt is actually sigma square into 1 plus theta square plus phi theta sigma square upon 1 minus phi square. This is what the variance of xt. You can verify that. So that's what this is. This is simplified. The sigma square into 1 plus theta square plus phi square. I think, yeah, phi square will come on that other side. That is 1 minus phi. So sigma square into 1 plus theta square into 2 phi theta upon 1 plus 1 minus phi square. So now you can see from this formula, it is very easy to see that the variance, will not be positive when you have absolute of phi less than 1. If absolute of phi greater than 1, this will be negative. So, that is not allowed. So, because the way we need absolute phi square less than 1 or absolute of phi less than 1. This is already the case with the AR1 model. So now the autocovariance function is given by, you can see that the autocovariance function gamma h is actually given by, we can go back and then start computing the autocovariance function. Like what we have computed the variance, we can also compute it. So here, what is the process? Xt equal to phi xt minus 1 plus zt plus theta zt minus 1. And you compute the covariance between xt and xt minus 1. So if you compute that, this is essentially, because mean is 0, it's like you have to multiply xt minus 1 and then take the expectation. So it is phi into variance of xt minus 1, and you are multiply xt minus 1 zt, that is 0, plus xt minus 1, that is theta sigma square. And so what you have is, you have to substitute the variance formula over here and then simplify it, and that leads to this formula. So it's like that variance plus theta sigma square, that's what you have, variance plus theta sigma square, phi into variance, so phi into variance plus theta sigma square. So I have already proved it for you. That's your gamma 1. This is gamma 1 because this is actually first order covariance. Okay, so this is basically phi into variance of this. What is variance of this? Sigma square into 1 plus theta square plus phi theta. I think it is 2 phi theta, right? 2 phi theta. Right. I think there is a 2 was missing in my case earlier, sorry. Because if you remember the covariance, this is zt minus 1. Yeah, basically it's coming phi theta. The 2 is correct. You can check this, I mean whether it is. I think 2 is there. Yeah, 2 phi theta is there. You can verify this. Yeah, so what is happening is that I have, this is phi square, variance of xt minus 1. Variance of xt is equal to phi square variance of xt minus 1 plus sigma square plus theta square sigma square plus twice covariance, because you have xt minus 1 is 2 will be there. So that I was missing in my calculations. So actually here twice covariance is there. Here because it is variance plus twice covariance. So the 2 was missing. So you have basically 2 phi theta sigma square. I'm sorry. Okay, now on the same line, 2 phi theta sigma square is taken outside, and this is 1 minus phi square and plus theta sigma square. And that's what you have seen here. So this is what your gamma 1. And then in general, we can see that the gamma 1, you instead of this, if you now compute xt and xt minus h, so you can see that it is phi to the power of h and remaining all same. So you will get this is gamma 1 sigma square into 1 plus theta 1 plus phi plus theta 1 minus phi square phi to the power of h. So how this is obtained? This is obtained in a slightly different way. It is not obtained like what you have in the case of 1, but essentially the idea is same. What I will do is that in this case I'll multiply. So it's like I'll write this equation. So it's xt equal to xt minus 1 phi xt minus 1 plus zt plus theta zt minus 1 and multiply by xt minus h and take expectation. So what you get is expected value of xt minus h, which is gamma h, and that is equal to phi xt minus 1 into xt minus h plus expected value of xt minus h and zt and plus theta times expected value of zt minus 1 into xt minus h. So this is actually what happens that if h equal to 1, we have to h equal to 1 we already computed, so you should compute for h greater than 1. If h is greater than 1, the advantage is that this is going to be 0. This term is going to be 0. And if h is greater than 1, this term is also not going to contribute. So what is going to contribute is this. And that's what you are seeing. So you have, if you look at this, you can see that h equal to 1, then you can take expectation. So that is what, so I am multiplied by that equation and then take expectation for h equal to 1. So you can see that this is gamma 1. I am putting it for h equal to 1. So this is gamma 1 minus phi gamma 0 is equal to theta sigma square. You see that this is slightly different from AR1. H equal to 2 and this will be 2. So this is gamma 2 minus phi. This will be gamma 1 because I have 2 here. And these are all 0. So you can see that for h greater than 1, that means 2, 3, etc., gamma h is equal to phi of gamma h minus 1. That's what I got here. If you look at this, this is like, if you, this you can see that for gamma h is equal to phi gamma h minus 1. This is h minus 1, this is h. So these are all 0 for h greater than 1, because h greater than 1 means you have 2, 3, etc. So this will be 0. This is also 2, 3, etc. So this will be 0. So you have this equation, exactly same as what you have here. So now the rho h, so if you divide by gamma 0, this equation, what you get is in terms of ACF function, rho h is equal to phi of rho h minus 1 for h greater than 1. And h equal to 1, this you have this equation. So now you can simplify and then we can get all the autocorrelations. So what is that we can see that the ACF of ARMA 1-1 model behave very much like AR1 model, except that the exponential decay start with lag 2 because it's not starting with lag 1, it is starting with lag 2. And the ACF of ARMA 1-1 model does not cut off at any finite lag. This is about ACF. Why? Because ACF has this gamma h is actually phi to the power of h. And you have to divide by gamma 0. which will be a constant, but you have this h term. So it is not cutting off, because for every h, this contribute. So you have this. Similarly, it is possible, now we can also find the partial autocorrelation function of a ARMA 11, which has similar behavior after lag 1 of a MA sequence. So in summary, the stationarity condition of ARMA 11 model is same as that of AR1 model. What is that? Absolute of phi less than 1. So what is the gamma h? Gamma h means it is like, rho h. Rho h is gamma h by gamma 0, and your gamma h is here. So you divide by the gamma 0. Gamma 0 we already obtained. What is gamma 0? This is gamma 0, which is written here. So you have the gamma 0, you divide by that. So once you divide by that, you get this particular one. So this is what rho h. So rho h is equal to some quantity multiplied by phi to the power of h minus 1 for h greater than or equal to 1. This showing is not a great thing, because we already obtained gamma h, we already obtained gamma 0, you have to just divide by that and get this. So notice that the general pattern of rho h is not much different from that of an AR1. Hence it is unlikely that we will be able to tell the difference between ARMA 11 and the AR1. So this is what I wanted to tell you. Because you see, the autocorrelation function behavior is more or less very close to that of AR1 or AR. So in fact, you can see that AR and ARMA, the autocorrelation behavior is very close to each other. So we may not be in a position to distinguish. So hence it is unlikely that we'll be able to distinguish difference between ARMA 11 and AR1 based on ACF alone. Okay, here I want to show you the picture of the series. For example, this is simulated. Like for example, if you take phi equal to 0.5 and theta equal to 0.5, you get a picture like this. For the ARMA model simulated, it is like this. And this is of course with mean 0. And 5.5 means it is simulated like this, and minus 0.5 simulated like this, minus 0.5, minus 0.5 simulated like this. So this is basically the ARMA 11, and its ACF, PACF look like this. So you can see that you can't really conclude from the PACF to the AR part. But something can be said, because if you look at the PACF, you see that after lag 1, it behaves like AR1. Lag 1 we cannot say AM, so what you have is, so that much we can say. So that's what happens here. After lag 1, this behaves like AR1. So this is for h greater than 1. Where h equal to 1, it can happen anything, because that depends on the coefficients. Right now the coefficients are chosen in such a way that it is value is here, it could be here, it could be there, it could be even smaller than that. But after lag 1, you can say that it behaves like a AR1 model. This is looking at PACF. Similarly, if you look at ACF after lag 1, you can see that it is that of an MA series. So you can look at that after lag 1, only one of them will be significant. So that is what the series. So identification of ARMA order is generally done. The ARMA PQ model is difficult to interpret, as the dynamic is much more complex. So it is difficult to infer P and Q from the ACF and PACF. However, we can still use the same approach as before. That means what we do is that look at ACF and PACF. If it is a pure AR or MA, it is fine. Now, if it is not, obviously pure AR or MA, fit a lower order ARMA model. Maybe start with an ARMA 11, because you can actually identify the order of PACF, you can identify the significant ACF order and PACF order. ACF order you attach with MA, PACF order you attach with AR, and then start with that ARMA model. And of course, from a competing set of models, we need to select the one which we will discuss what criteria can be used in such a situation. Well, if you are using a software R or something, software will actually identify a series for you, because there is a auto selection procedure. So auto ARMA will automatically identify which is the best model. So in case of smaller value NP, it may be possible to something, otherwise we cannot say. Okay, thank you.